Okay, in this video, let's continue the discussion of section 3.1 functions. We already discussed the function, domains, and when it is defined and when it is not defined. Okay, and now let's talk about the algebra among functions. From the sum, difference, product, and quotient of two functions. Okay, so first let's see the example. Assume we have function fx, which is x squared plus 9, and gx is 3x plus 5. Then we can see that x squared plus 9 can plus 3x plus 5. You can add these two functions together, or you can add these two expressions together and form a new function. Okay, so you add these two expressions together and you get a new function, and this is considered as the sum of two functions. Okay, and also remember, we know how to do product of two polynomials. So you just have term by term multiplication. X squared times 3x is 3x cubed. X squared times 5 is 5x squared. 9 times 3x is 27x. 9 times 5 is 45. Okay, and this one is considered as the product of two functions. Okay, so that's like the starting point of the algebra. What is algebra? Sum, difference, product, quotient of numbers. That is algebra. And here we are talking about the algebra among functions. So definition. If f and g are functions, the sum of f plus g. Check here. This letter f represents the function f, the function, but fx represents the value of function at x. It's different. So this itself already represents, there is a rule like the law 20, the law 2002. So you just the name. Okay. When you have the sum of f plus g is the function defined by the new function f plus g. Okay, so we have a new function, and then we're going to evaluate new function at x. The value of the new function at x is defined to be the value of f at x plus the value of g at x. Okay, so you have a name, the sum of the name at a certain point. It's the sum of the two values at the same point. These two concepts are different. Here you add two functions. Here you add two values. Okay. And you see here, f has a domain, g has a domain. Now your x must belong to the domain of f and the domain of g. So the domain of f plus g is the domain of f intersect domain of g. Your x should be in both domains. Okay, so this is a sum. The difference of f minus g is the function defined by the similar way. F minus g of x is fx minus gx. We call it a pointwise difference. 3. The product of f dot g is a function there's no off, the sum, the difference, no off, sorry. The product of g is a function defined by f times g of x is fx times gx. So here I should copy this, copy it here, copy, and also copy it here. So whenever you see fx, gx appear together, then x should belong to the intersection of two domains. And for the quotient f over g is the function defined by f over g of x is fx over gx. Again, you're going to copy this condition. The domain f over not the intersection. It's a quotient. The difference product quotient in the is equal to the intersection. So the domain f minus g is equal to the domain f intersect domain g. The domain f times g is equal to the domain of f intersect domain of g. Here, the domain f over g is equal to the domain of f intersect the domain of g. One more thing, you have denominator. Whenever you have denominator, be careful. And intersect gx is not equal to 0. So if the value of x make gx equal to 0, you have to remove it. Okay, so when you have quotient, whenever you have denominator, you need to make sure the denominator is not equal to 0. Okay, so that's the straightforward definition. Okay, so let's see. Actually, when you have a concrete functions, those sum, difference, quotient, product, even more simple. Let fx be 1 over x plus 2, gx be x over x minus 1. Find the following and determine the domain. Okay, so first let's see f plus g of x. F plus g of x, well, let's just follow. It's fx plus gx. It's 1 over x plus 2 plus x over x minus 1. If we don't have any further target, this is good enough. There's no way, I mean, it's not necessary to simplify it. But sometimes, or in most moments, we possibly will write it as one ratio. So let's continue it. We multiply the first rational function by the denominator of the second one in order to find the common denominator. And second one, we multiply top and bottom by the denominator of the first one. So now they share the same denominator. And you added them, so this is x minus 1 plus x squared plus 2x. The final answer will be x squared plus 3x minus 1, x minus 1, x plus 2. Okay? This is a function, the sum of two rational functions. And the domain is x is not equal to 1, and x is not equal to negative 2. X is not equal to 1, it comes from x minus 1 equal to 0. X is not equal to negative 2, comes from x plus 2 is equal to 0. And this is exactly the intersection of them. This has a domain, this function f has a domain x is not equal to negative 1. This one has domain x is not equal to 1. So you get the intersection means and. Intersection means and. Okay, so let's and difference you just change here to be the negative. It's not difficult. Let's see the product. The product of two functions is fx times gx. So you get 1 over x plus 2 times x over x minus 1. It's just x over x plus 2 x minus 1. Well, the same thing, the domain is x is not equal to 1 and x is not equal to negative 2. That's the domain. Okay, so now let's talk about the interesting part. F over g of x is fx over g of x. Fx 1 over x plus 2, gx x over x minus 1. We know that when you divide a rational expression by the second rational expression, you change it to the multiplication, and it looks like this. This one, let's talk about the domain. The domain is the domain of x, fx. X cannot be negative 2. The domain of g, x cannot be negative 1, positive 1. And the 0 of g, x cannot be 0. Okay, so you see x cannot be equal to 0 appears here. When x is 0, denominator is 0. X is not equal to negative 2 comes from this part. But this one is in the numerator. Technically it's allowed in this expression, but since this function is related to g of x, whenever you have g of x in the original definition, x equal to 1 is not allowed. If you don't have these steps, you directly write down this rational function. The domain only removes 0 and -2. Since your expression comes from g of x has domain, so you have to remove 1. Okay, so that's a small subtle point. Even though in the final expression it looks good, 1 looks good, but it is not in the domain because from the origin it's not in the discussion. Okay, so let's see. In the on page 210, there is a summary. There's a summary. In the summary part, the 3 topics. One is a function. Function is a relation. It is a special relation. Given x, there is a unique y such that y is equal to fx. F is a relation, okay? So given one input, there is only one output. So we either write xy or xfx. One input, one output. You cannot allow multiple cell phone numbers, okay? And the domain is a set of all x. The range with whatever requirement from the special problem. So that's why we put the dots to represent. There's some some conditions about some conditions from the questions. The range is fx, all possible fx. X is in the domain. X is in the domain. Okay, so that's a range. And sometimes you have explicit or implicit functions. You have implicit and explicit. How do you determine the explicit function? How do you determine the implicit functions? Okay, so that's a function. Function is a relation. What is a function definition? Function has domain, has a range. How do you determine domain and range? And you have 2 ways to represent the function from the equation. Basically, this is come from the equation. You have implicit equation, implicit function and explicit function. Explicit function means y is on the left side, and certain expression about x on the right side. Given x, you do some operation, computation, you can directly find the y. Okay. Implicit means you have to do some algebra computation in order to solve for y. Okay. And the second part is unspecified domain. Sometimes a function is defined if f is defined by an equation and the domain is not specified. domain is not specified, then the domain is taken to be the largest set of real numbers for which the equation defines a real number. Okay, so basically, if the domain is not specified, then you just get the largest possible input. Whenever input makes sense, you put it in the domain. Okay, so that's a unspecified domain. So for example, if you have a square root of x, the domain will be x greater than or equal to 0, because in this case, for the non-negative number, square root of x makes sense. If you have a negative number, we're talking about the real world. If there's no special requirement, all the functions have the domain in the real world, not the complex, real world. So in the real world, square root of x is not defined as a negative number. So this is the largest possible set, so that all the points is defined for the function. Okay? Function notation. Function notation means this one. This is a function notation. Y is equal to fx. F is the symbol of function. It's kind of like the name of function, or the name of the law. And x is independent variable. Y is dependent variable. X is independent and Y is dependent. Okay? And Y is also called the image, or fx is called the image, is the image. Sometimes you call value of the function at x. Okay? So that's the summary. It's on page 210. So in this section, we set up the basic vocabulary. We are going to use those vocabulary in the future, actually in the whole classes. Okay. It's end of the section 3.01. In the next video, we will start section 3.2, graphs. I finish this video and start with another video. Thank you.